Welcome back. In this module, we will briefly discuss convergence to steady state. Okay. So, I am given a positive recurrent irreducible aperiodic is now it is necessary, all right, aperiodic DTMC. I want to show that limit n tending to infinity Pik(n) is equal to pi k, all right, which is your stationary distribution. Pi k is just as we constructed earlier, right, expected number of visits to k over expected TJJ. Okay. Now, this we proved for aperiodic irreducible positive recurrent DTMC. We proved this convergence using Blackwell's theorem, all right. Now, this Blackwell's theorem itself is a really big hammer, all right. It is the general proof of Blackwell's theorem is something that we did not do. So, we have used a big theorem which we have not proved to prove a relatively easier theorem in about Markov chains, all right. So, let us remedy that by actually deriving this convergence Pik(n) is equal to pi k using some elementary arguments. In fact, the trick we are going to use is called stochastic coupling. Okay. This is also from Grimetz-Scherzecker section 6.4. Okay. So, the basic idea is the following, maybe I will not go into all the gory details. Okay. The idea is this, okay, let us say B the Markov chain under consideration, okay, DTMC under consideration. Xn is known to be positive recurrent irreducible aperiodic, all right. And the idea of the stochastic coupling is to consider an independent Markov chain Yn with the same transition probabilities. Okay. So, in the same sample space, so I have Xn evolving on some sample space omega Fp, all right, on some probability space omega Fp. I am starting in state I, right. So, I want to look at Pik(n), right. So, I have x naught equals I, okay. So, my X Markov chain, which is the Markov chain of interest, is starting in state I. I want to look at the probability of being in state k, the X Markov chain being in state k. After a very large time n, I want to show that Pik(n) converges to this pi k, right. So, what I am going to do is consider an independent Markov chain on the same probability space, all right, with the same transition probability. So, the probability of going from state j to state L is the same for both the Xn Markov chain and the Yn Markov chain, but I am going to take Y naught as some j, okay. So, they are independent Markov chains, they have the exact same transition probability matrix, transition probability kernel, and I am going to start them off in different states, all right. So, the stochastic coupling is a standard trick when dealing with Markov chains. You basically look for, so you are starting in two different states and these Markov chains just jump around and evolve, and you look at a time, the first time when both these Markov chains are in the same state, okay. So, to give you a picture, say this is all states, okay, and this is time. My Y Markov chain is starting at j, okay, it's jumping around, all right. And my x Markov chain, which I will draw during, sorry, let us say this is my x Markov chain. So, this is x naught, x1, x2 and so on, all right. X naught is j. Sorry, I think I said x naught is I, right. So, let me say x naught is I. And then I say y naught is j, okay. And then this guy also jumps around. Sorry. Okay, and at this point they are in the same state, okay. So, these are the various, so time is various integers, right. So, at this time they are in the same state, okay. The key issue in stochastic coupling is that once these two Markov chains meet, they start in different states and they jump around and they meet at some time. The first time they meet, after that they are stochastically coupled, in the sense that the distribution of the further evolution will be statistically identical, all right. Of course, I am not saying that the blue curve and the black curve will stick together, I am not saying that, okay. I am saying that the distribution will be the same, okay. By the way, so the black curve and the blue curve, see I am looking at only integer time. So, something like that is not a point of, I mean it is not, you should not look at the chain as having met, okay. So, you should only look at, I am just drawing some lines here, maybe I should not connect them using these continuous lines, but you see what I mean, right. This is j, this is some other state, this is some other state and this is some other state. There is actually nothing here, okay. So, this excuse me. So, you do not look at these as meeting points, this is a real meeting point, okay. Okay, that is my t, the time of first meeting, and then of course this black guy goes on and on and this blue guy goes on and on, okay. But the point is that I mean they do not have to evolve together, but the distribution of the evolution after this time t will be statistically identical. That is the whole point of stochastic coupling, okay. So, the argument for this convergence is as follows. So, xn and yn are these Markov chains. So, they have the same state space, same transition probability and all that. You define Zn as the tuple xn yn, okay. So, this takes values in S cross S, okay. Xn takes values in S, Yn takes values in S, Zn takes values in S cross S, okay. What you can show, I will not get into all these proofs, is that can show Zn is a DTMC with state space S cross S. Transition probability, if you look at probability Zn plus 1 equals k comma L, given Zn is equal to I comma j, this will simply be probability that xn plus 1 equals k given xn equals I and times probability that yn plus 1 equals L given yn equals j, all right. This is because the Markov chains are independent, correct. So, this is nothing but your P I k, and that is your PJL, right. So, the transition probabilities of Zn Markov chain is just Pik times Pjl. By transition probability I mean this guy, right. We can also show that Zn is irreducible and aperiodic. This comes from the corresponding properties of Xn and Yn. Okay. This requires a proof, all right, but it can be shown. So, maybe I should say can be shown state space blah 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 with the transition probability. Now, question is, does Zn, this Markov chain Zn, have a stationary distribution? On S cross S, right. So, can I have, so I want to have nu is equal to nu ij, ij belongs to S, right, I and j belongs to S cross S. Answer is yes. You take nu ij, the steady state probability, sort of the stationary distribution of the X Markov chain being in I times the Y Markov chains being in J. Okay. You just propose this as a solution, okay, this product of the two stationary distributions. You can show that this nu ij is a stationary distribution for the transition probability kernel Pik times Pjl, okay. And for any Markov chain, if you do manage to find a stationary distribution, we already know that that stationary distribution is unique, right. We also get positive recurrence for free, correct. So, this must be unique. So, I am just proposing a solution nu ij stationary distribution for Z, the Z Markov chain as pi I times pi j. You can verify that this pi I times pi j satisfies the balance equations for the Markov chain Pik times Pjl, Markov chain Zn with transition probabilities Pik Pjl. So, this is unique by the theorem that we know, and Zn is positive recurrent, right. So, we get that for free. Remember, if you, the moment you find a stationary distribution, that is the only solution to pi is equal to pi p, and the chain is positive recurrent. So, I am proposing nu ij equals pi I times pi j as a solution. I verify that this satisfies the balance equation for the Z Markov chain. Then this solution must be unique, number 1. Number 2, I get positive recurrence of Z for free, all right. Now, this is great. Now, the coupling trick works as follows, okay. So, we are taking x naught equal to I, y naught equals j, right. I am starting in different states. So, z naught is simply I comma j, okay. Define t as minimum n such that xn equals yn. Okay. This is my, so what am I looking at? So, I let these Markov chains evolve, right. So, I start the X Markov chain from I, Y Markov from j, and I let them evolve, and at t they meet, right. T is the first time they meet, all right. what you can show is that can show t is a stopping rule, stopping time with respect to xn comma yn, which is just zn. And since this this is a Markov chain which is positive recurrent, z we know to be a positive recurrent, we have shown that z is positive recurrent, we can show that t is finite with probability 1. Why is that? See, I start in state ij, z naught is ij, I want to get to some state which look like s comma s, right. What we can show is that we will get there in finite time, okay, because the chain is positive, z chain is positive recurrent. In fact, you can show that expected t is also finite, okay, because it is a positive recurrent chain. Now, after t, the evolution of the Markov chains will be statistically similar, okay. Key idea, for n greater than or equal to t, the evolution of xn and yn will be statistically identical. So, what I am seeing is that once these guys have met at this point, the probability that at any time beyond this t, let us say at this point, right, the probability that the x Markov chain is in some state L will be the same as the probability that the y Markov chain is in that state L, okay, and this will be true for any time after this stopping time, okay. This is because of again strong Markov property, okay. You will agree with me that if I start two independent Markov chains at the same state at time 0, okay, let us say I have two independent Markov chains starting at time 0 at the same state, okay, with the identical transition probabilities, then you will agree that the distribution of the states at time greater than 0, the probability of let us say the first Markov chain being in state L will be the same as the probability of being the second Markov chain being in the same state L, let us say at the time t equal to 13, okay. But that is not the scenario here. I am not starting at time 0, I am starting at time 0 at different states, but at some point they have met and that is stopping time, right. And because of strong Markov property, the further evolution will be statistically identical for these Markov chains, okay. This is because of strong Markov property, okay. So, with this we can bound, we can prove that pi k n goes to pi k, okay. The argument is as follows, you look at pi k of n, okay. This is the, so let me look at, let me say this is the probability that xn is equal to k, right, given x naught equals I, all right. This I can write it as probability that xn equals k t less than or equal to n, right, when x naught equals I plus probability xn equals k t greater than n. All right. So, this is before stopping, right. See, by stopping I do not mean that everything stops, right, I just mean before the stopping time, right, and this term is after the stopping, where the first term is after the stopping. Okay. Now, the key issue is that this will be same as probability yn equals k, t less than or equal to n, right, given. So, this is I can write y naught equals j. Okay. So, maybe a better way to denote all this. So, maybe I should define you know, I will define I'll define notation just now. Just forget this for a minute. So, you are starting at z naught equal to I j, right. So, I am going to call p dot of given z naught equals I comma j as p, let me call this p I j of dot, all right. So, this is just convenient notation for me. Okay. I know that p I j t less than infinity is 1. Okay. Now, consider p I k of n, which is the which I can write as p I j of x n equals k, right. This is just p I j x n equals k n less than or equal to t plus p I j x n equals k semicolon n greater than t, all right. N less than t, n greater than or equal to t. Okay. And this bit is after stopping. Let me say after x n and y n meet, right. So, this will just be p I j x n equals k n less than t plus the key idea is this will be p I j y n equals k, right, because after they meet the probability. So, you are looking at n greater than or equal to t, right. After they meet the probability that x n is in state k, the same as the probability that y n is in state k, right, because they have the same transition probability and they have already met. You are using strong Markov property. Okay. So, this I can say less than or equal to, I can just call it p I j t greater than n plus p I j I will just write y n equals k. Okay. So, what have I shown? I have shown that p I k n step transition probability is less than or equal to p. So, what is p I j y n is equal to k? This would be p j k, right, n step transition probability. The probability that you are in state k having started at j, remember the y Markov chain starts at j, right, p j k n plus p I j, this probability, right, probability that t exceeds n, all right. Similarly, you can show the exact opposite also. You can just interchange the roles of this I and k, I and j, and simply get p j k n is less than or equal to p I k n plus Pij t greater than n. Okay. So, this implies the, if you look at this difference, Pik n minus Pj k n, look at that difference, this is less than or equal to Pij t greater than n. Okay. This implies, now if you send limit n tending to infinity, so this, the right hand side will go to 0 as n tends to infinity, right. That's because you are going to this stopping rule, it's a legitimate stopping rule, right. You are going to the states, the Markov chain Z is recurrent, so you are going to, the states are going to meet eventually with probability 1. So, the probability of not stopping until time n, the probability that the stopping time is bigger than n goes to 0 as n goes to infinity, because t is a legitimate stopping rule. This implies limit n tending to infinity Pik n minus Pjk n is equal to 0, all right, which means that limit n tending to infinity Pik n is equal to limit n tending to infinity Pjk n, all right. That we could have seen actually even from these two equations, right. You can just you can actually prove that they are equal. So, that is good. So, what does this show? It shows that the probability that I am in state k after a long time does not depend on where I started, the I or j, it does not matter, right. So, memory of initial of x naught is lost, right. That is good news, but we have to prove that this limit, so whatever this limit is has to be so only a function of k, right, but we have to show that this limit is in fact pi k, which is a solution to pi is equal to pi p, right. So, that you can argue as follows. So, you just look at pi k minus Pjk of n. Okay. So, if this limit exists, so if this limit exists, I know that they have to be equal, right, if they exist. So, I am going to consider this, I am going to write this as sum over pi I Pik n minus Pjk n, sum over I. So, this is true because of this if you look at this bit Pjk n, so sum over pi I is equal to 1. So, that works out, and this is because of the balance equations, right. So, this is fairly clear. So, if you take now if you take limit n tending to infinity, so I have to show that the limit actually exists and it is equal to pi k, right. I have just shown that so far I have been solid here, right. I have to show that this limit exists, right. If it does exist, then the memory of initial states is lost. So, limit n tending to pi k n tending to infinity pi k minus Pjk n be equal to limit n tending to infinity sum over I belongs to S pi I Pik of n minus pjk of n. All right. Now, each of these terms is going to 0, right, as n tends to infinity. That I have shown because that I have shown here, right. So, this difference is going to go to 0, but I have a sum which is a potentially infinite sum, right. So, if I take the limit inside I get 0, okay, but I have an infinite sum outside. So, you need to justify why you can take the limit inside. In this case it works out because of dominated convergence, okay. You can just say this is 0, okay, this requires some justification, okay. So, you can write limit n tending to infinity pi k minus pkj of n is equal to 0, okay. Therefore, you have convergence of pjk of n to pjk of n equal to pi k. This is true for all j k in S, okay. So, it is pretty powerful, this technique, as you can see. I have not used any Blackwell's theorem or any such big hammer like that. The main trick is coupling, right. So, I have considered this two tuple of Markov chains xn and yn both independent. They start in different states. I have to prove that the Markov chain Zn itself is positive recurrent by explicitly finding a stationary distribution. So, I am guaranteed to meet in finite time, and after you meet, you know, these two terms turn out to be equal, right. That is the key step, and then it is just real analysis really, okay. So, we have shown that Pijn goes to 0, Pijn goes to pi j as n tends to infinity, right. So, the periodicity the aperiodicity is used, you know, you have to use aperiodicity to show that of xn and yn to show that Zn is irreducible and aperiodic, and no, only then without aperiodicity you will not get this result, okay. I will stop here.